Hello everyone. Welcome to my talk which explores the outlandish idea of adding compute to low-flying satellites which are currently being deployed to build mega constellations offering internet from space. Starlink, Kuiper and Telesat are three of many such proposals which are currently in different stages of development and deployment. While for the first phase, Starlink plans to deploy more than 4,000 satellites in low Earth orbit or LEO, which is only a few hundred kilometers in height from the Earth's surface. Their long-term plan is to deploy more than 40,000 satellites. We asked the question, what if we can add compute to each of these satellites? While there are some interesting use cases, as we'll soon see, even the feasibility of such a deployment is not clearly known at the moment and calls for a more thorough analysis than in our current work. But looking at the brighter side, with this model, no matter where you are, compute follows you. Let us now look at the first interesting use case. This is the current deployment of a large CDN in the US. Compare this to their footprint in the African continent and Middle East. In large parts of the world, CDN edge latencies still exceed 100 milliseconds, which affects end-user experience. Prior work has shown even tens of milliseconds of additional round-trip latency deteriorate web browsing page load time substantially. Fast online multi-tenant gaming QoS depends on latency. Further, for new upcoming applications like augmented reality, latencies beyond small tens of milliseconds are prohibitive. More broadly, many such networked applications that depend on low latency for rich interactivity are being referred to as tactile internet applications. Many of these applications depend on data fetched or processed from nearby edge computing infrastructure with tight latency requirements. Let us see how adding compute to satellites can reduce this edge latency. These are the observer's fields of view in different parts of the world for Starlink Phase 1. X-axis represents the panoramic 360-degree view of an observer, while y-axis represents the altitude or elevation. Different colors of satellites signify different shells, and the blue shaded region marks minimum elevation restrictions. As we see here, even with a minimum elevation of 25 degrees, there are many satellite choices available at each location. One satellite may not offer a large amount of available compute. So this plot quantifies the number of Starlink Phase 1 and Kuiper satellites reachable from a ground location at any time. Starlink Phase 1 will have 4,409 satellites, while Kuiper plans to deploy 3,236 satellites. The solid lines denote average, while the dashed lines denote minimum and maximum over time. For Kuiper, more than 10 satellite servers would be reachable from any location for most latitudes Kuiper services. For Starlink, more than 30 satellites are reachable from almost all locations at all times. Typically, more than 40 satellites are reachable. In-orbit computing could serve latency-critical application needs by providing low-latency compute access everywhere on Earth. This plot shows the round-trip times from ground locations at different latitudes to Kuiper and Starlink Phase 1. For each constellation, we compute the RTT from a ground location every minute over 2 hours and use the maximum value across these measurements. We do so for the nearest reachable satellite as well as the farthest directly reachable satellite. The nearest reachable satellite is roughly within 4 milliseconds at most latitudes for both constellations. Of course, these numbers are computed accounting for only propagation delays, so true latencies will be somewhat higher. A variety of applications involve multiple users participating in an interactive activity, such as online gaming, collaboratively playing music, learning in a shared online classroom, or more broadly, immersion in the same virtual environment. In these applications, often the multi-user group's experience is contingent on every participant receiving low latency connectivity to the server hosting the application, which we shall refer to as the meetup server. Even using the Starlink LEO constellation to connect 3 users in West Africa to the nearest Azure terrestrial meetup server, we find that the RTT would be as high as 46 milliseconds. On the other hand, the RTT to a meetup server hosted using in-orbit compute on the same constellation would be 16 milliseconds, an almost 3 times reduction. We assume that user terminals can communicate directly via satellites without any gateway intervention, like in Starlink. Many applications like Earth imagery, weather observations, and remote sensing generate their data in space. Satellites performing imagery and sensing are capable of multi-Gbps data production, but their sensing time is limited by data transmission capacity to ground stations. Pre-processing this data using in-orbit compute could increase sensing time and decrease the bandwidth cost of downloading this data and further processing it terrestrially. This figure shows that more than a third of Starlink satellites are invisible at any time. These satellites are not directly within reach from any of the largest 1,000 cities by population. As intersatellite bandwidth is less constrained than radio downlinks, it allows these satellites to process data cooperatively, thus reducing the downlink bandwidth demands. Okay, having explored some interesting applications in this context, let us see whether satellite compute is even feasible. We compute a commodity server's weight and volume relative to that of a Starlink satellite. We use a high-end server S with 64 cores and up to 2 terabytes of memory. Compared to the latest Starlink satellites launched, the weight is 6% of a satellite's weight and the volume is 1%. These are significant costs but not prohibitive. Of course, this mass and volume overhead means increased mass or fewer satellites per launch. Space hardware needs hardening against ionizing radiation hazards. But ongoing research hints at the possibility of using commodity hardware below the inner Van Allen radiation belt and instead rely on software hardening. For example, the HPE spaceborne computer aboard the International Space Station operating at roughly 400 km height is commodity hardware without any specialized hardware frame. Additional power consumption is a big challenge given satellites already use a combination of solar arrays and batteries to satiate power demands. The high-end server S operating between 225 watts and 350 watts would consume between 15% and 23% of this power. This is quite large, but if necessary, lower wattage servers could be used, or a larger solar array and battery could be built in to support this additional power requirement. Another related problem is the increased heat generation. Heat is harder to dissipate without an atmosphere, so additional radiators or thermoelectric harvesters may be necessary. Such additional components will also increase the mass per satellite. Starlink satellites will have a life of 5 years, which is a bit longer than the typical data center server life. If a satellite server malfunctions before its expected life, unlike in a data center, it would not be replaced immediately. However, operators continually replenish their satellite fleet and maintain backup satellites per orbit. Thus, even with a substantial fraction of servers failing, a large LEO constellation could continue to provide valuable in-orbit computing resources. How does in-orbit compute compare to terrestrial compute in terms of cost? Considering the per kilogram launch cost, weight of the server, and the amortization over 3 years, a coarse estimate is that a satellite server would be roughly 3 times as expensive as a data center server. We do not, however, take into account the benefits of scale. Last but not the least, the dynamic behavior of LEO constellations poses a challenge. If a satellite is now over eastern Brazil, in 6 minutes it will already reach Africa, crossing the entire Atlantic, traveling more than 500 kilometers per minute. Due to this dynamic behavior, a particular meetup server is only reachable by clients for a few minutes, after which a handoff is needed to a different satellite. This handoff is different from cellular or Wi-Fi handoff due to the additional mobility of the network infrastructure. Note that trajectories are highly dynamic, yet predictable. By virtue of regular handoffs, a series of LEO meetup servers can expose to clients an abstraction similar to geosatellites, stationary operation at roughly the same location over time. The naive Minmax approach for selecting a meetup server picks the latency optimal satellite at each instant. It minimizes the maximum latency across a set of clients connected. However, Minmax suffers from potentially frequent handoffs to successor meetup servers. An alternative heuristic, Sticky, prioritizes stationarity by planning ahead, leveraging predictable satellite motions. It computes the set of meetup servers that provide latency within 10% of Minmax. orders them by the longest time until a handoff. Among the top 5, it picks one which would result in the least latency for handoff to its successor. For the 3 users in West Africa use case, Sticky substantially decreases the frequency of handoffs at the cost of less than 10% latency inflation, while the latency for state transfer to the successor remains similar across Sticky and Minmax. To conclude, the mega constellations can host sizable aggregate compute, thus enabling low latency compute access from everywhere at any time. This can be attractive for some applications, given many potential issues are not too prohibitive. Yes, we know this is an outlandish idea, but what is your take on this? Thank you for listening.